So good morning, everyone. Thank you for attending this presentation. Can you hear me very well? Yeah, perfect. So definitely today is a very special day for me. So because 10 years ago, when I started my first position as assistant professor in Chile, probably I will never have imagined these moments for that reason. Thank you for attending these presentations. So I'm very lucky to be here. And today I want to introduce you to my research fields, focus on cell healing, bituminous material to promote more sustainable and resilient road under the umbrella of the RILEM associations. So before I begin my presentation, I would like to extend my gratitude to all the international members involved in the jury. It's a pleasure for me to receive this award of the president founder of RILEM, Robert R. Medalist. I really appreciate this award and the opportunity to share some details about the road science with the RILEM community. Thank you so much. So go ahead. So the road also a social concept. So because everyone here use a road to transport every day. So however, daily conditions affect the roads for the sun irradiations, rainwater, pollution, traffic. And they need maintenance to stay in good condition, like a body when you go to the doctor. So during the next few minutes, let me tell you some details about these interesting black materials. So, for instance, the roads are made using bituminous materials, including a very complex sticky material black. This is the name is bitumen. It's very complex materials, but you have, for example, also asphalt mastic, the combination with bitumen plus small particulate aggregates and asphalt mixture. The asphalt mixture is a composite material composed to aggregate and bitumens as the most important material to road pavement construction around the world. 90% around the world are made using asphalt mixture with the principal materials. For example, only in UK, over 20 million tons of asphalt mixture is produced every year to maintenance and construction purposes. Definitely here, we have a big problem because we can produce CO2 emissions. The previously you mentioned the CO2 emission problem in the concrete business, but the other problem is exactly the same. We need our science commitments in RILEM and another association in order to net zero emission by 2050. And for that reason, it's necessary to reduce the emissions, introducing very new technology. At the same time, the big problem in the road is a multi-scale problems, but the road cracking is a multi-scale problem, basically, and depending on the scale, the solution can be different. In the big ones scales, you have potholes, probably you know. It's pretty easy to solutions, incorporating asphalt mixture, but this problem is huge, difficult when you evaluate the material for molecular level, when you have different components, saturated, aromatic, or resin asphaltenes. The asphaltene material rate is reduced and you incorporate new solutions. To reduce this problem, in this keynote speaker, so emerging cell healing technology extend the road surface life. So basically, let me show you more detail about that. So at this point, the question is, what is a cell healing asphalt? The key is the bitumen viscosity. But bitumen is a thermoplastic polymer with thermosensitive properties. Basically, bitumen is a solid at the road temperature. But when you increase the temperature, it can flow and close the opening the crack autonomously. So basically, we can produce a cell healing materials. A bitumen is a cell healing material itself. But to increase this application, this property, we need to design different emerging technologies using extreme cell healing technologies. To promote the healing properties of the bitumen, we can use 3 different extrinsic technology classified in 2 different groups. So the first group is concerning to the external heatings. Here, you can use induction heating, basically for the asphalt mixture contains several ferromagnetic additives that are exposed to electromagnetic fields. Basically, you can reduce the temperature of the bitumen and you can promote the flow inside the open the crack autonomously using this technology. Another one is the microwave radiations. You can incorporate metal or no, with and without metal is effectively. It's exposed to electromagnetic field using a radiation fields. The next technology is encapsulated rejuvenator, is an autonomous approach. Basically, you can produce capsule with rejuvenator. Rejuvenator is an extended oil with very rich components, with aromatic components to stabilization of the Martinez-Faltin ratio inside the bitumens. The broken capsule can release contained dereguminators inside the asphalt mixture that reduce the viscosity and improve the aged bitumen by diffusion sealing the open microcracks. So basically at this point, using this technology, but the concept of the road maintenance and preservation over time has been refined. Basically, we need to extend the safety life of the road, incorporate the different emerging technologies to extend the safety life, to reduce the CO2 using the asphalt mixture production and maintenance. At the same time, if we evaluate the publication on this topic, in the recent year, the last 15 years, we can conduct that this topic has grown exponentially. Let me show you. The self-healing asphalt, in summary, and this technology are a hot topic in the field of the raw materials. I strongly believe that using waste source combined with the valorization process, you can design new material for asphalt and the new material for bituminous materials. So basically, at the same time, you can contribute to the different sustainable objectives, number 9 and number 11, to produce transportation infrastructure, advanced transportation infrastructure, combining material science, civil engineer, and chemical engineer to produce self-healing materials. This research about this big research can be carried out using 2 different topics. The first topic is concerning to the base on the heating technologies and waste valorization to produce self-healing materials. And the second one is using, by the action of the bio-based encapsulation healing engines to produce self-healing materials. Both topics are carried out using a material characterization techniques with multi-scale modeling to resolve both problems. For this presentation, I have selected 6 different projects to show you a brief overview of the research concerning to the self-healing asphalt. In the first part, let me show you a few examples concerning to the external heating approach. For example, we can use 3 different additives, electromagnetic additives, stable fiber from clean industry, steel shaping from manufacturing industry, and of the last turrets for the tire industry. But basically, all these additives can potentially be used in asphalt mixture for heating purposes. Obviously, when you study the material with microstructural properties, you can complement designs, you can incorporate the new materials inside the different applications, etc. During my time working in Switzerland, in EMPA, during my last year of my PhD, we designed the first self-healing material applied in the dense asphalt mixture. For this purpose, we use stable fibers and induction heatings. Basically, to evaluate these materials, let me show you. Well, first, they generate artificial cracking using mechanical testing, for example, 3-point bending tests. That's possible. You can use fatigue tests. It's dependent on your purposes. Then to use the pieces of the sample to piece together in this sophisticated support, and then heat them under the induction coil without contact. After the sample is heated for a few seconds, you can stimulate the bitumen inside the materials, and you can promote the flow autonomously inside the materials. After the sample is heated, after the sample cools at the room temperature, we can manipulate it and check that the crack has been healed. Let me show you. But obviously, we can must quantify the healing index before and after heatings using mechanical property, using different index in order to evaluate the cell healing properties. These samples contain fibers, stable fiber explicitly. So this is important to evaluate their distributions within the samples. For example, by using computed tomography. The recommendations after evaluating 1,000 tests is to short fibers in a low adhesion percentage with the diameter close to 0.2 millimeters. On the other hand, it is also necessary to evaluate the heating time of the sample heating by using microwave radiations in order to compare with induction technology. Thus, the effective amount and optimal times allow us to compare to microwave radiations with induction heatings. For that purpose, it's necessary to design pretty easy tests in the lab. Basically, in order to microwave oven, you can heat samples. Know your food, please. And after that, you can evaluate using a camera the temperature distribution inside the materials with a specific time in order to evaluate the close the crack autonomously by effect of the radiation using the microwaves. And also you can compare this result and this time and this energy with the induction technology also. So comparing both heating technologies has shown that microwave can achieve a higher healing index over time, but they can also affect the microstructure of the asphalt mixture. For example, you can produce hot spot when you expose the material to the high temperature. The recommendation is to use the induction heating and on-site conditions without affect the asphalt mixture performance. Another example is to use the steel shavings from the metal manufacturing inside the asphalt mixture. In design, everything is possible. All the ways can be used for asphalt healing purposes. In this case, at the same time, this additive can also be combined with the use of recycled asphalt pavement to produce more sustainable mixture. Basically, in this research, we comparison with both materials, the reclaimed asphalt pavement with a small addition of the steel wool fiber and steel shavings to increase the temperature inside the material by using these waste material aggregates. At the same time, we can use tight fibers to stimulate the materials, but the recommendation is this fiber is so complicated to work with that because it's necessary to produce several modifications in the mixing process to obtain a very good asphalt mixture. But it's possible to heal the samples. And also it's possible to use blast furnace dust for the steel industry. This is a small powder with metallic properties that is very good. You can reach a very good distribution inside the asphalt mixture at the same time, but it's possible to heal the samples until 100%. Concerning to the large scale application of induction healing, the most important example probably was carried out in 2010 in Netherlands, led by Professor Erik Langens. So in this process, we use, as you can see here, a big induction machine to heat the raw samples. Even though the technology is possible, and you can extend the surface life of the asphalt pavement by up to 50%, it is not very practical because a big induction machine is necessary to heat the asphalt under real conditions. In this moment, and the second example is the large-scale application recently in Germany. So you can see another more current examples. And these points, you can simulate on the real crack on the surface of the ropes. And after that, you can apply induction heatings in order to close the crack autonomously. At this point, the encapsulated rejuvenator technology becomes necessary and very useful for heal purposes without human interventions. In the next part of the presentation, let me show you a few examples concerning to the encapsulated rejuvenators resource. Under my visions, the following equation can define the preparation of the encapsulated rejuvenator for more sustainable roads. Basically, you can use biopolymer source to replace the polymer based on petroleum. You have used sodium alginate, glimmer arabic, craft lignin, ketosane, and carrageenan, plus several rejuvenators, alternatives to the conventional rejuvenator materials. You can use coconut, recycled oil from McDonald's, for Burger King, engine oil, and at the same time, you can produce specific rejuvenators by using thermochemical conversions, including pyrolysis, including hydrothermal liquefactions, to produce, for example, liquefied bio-oil or pyrolytic oil for end-of tires. Combined with the physical-chemical encapsulation methods, you can produce several biopolymer capsules with different purposes. You can produce polynuclear capsule, coated shell capsule, fibers. In summary, you can prepare different types of capsules by combining these material and methods. Due to the time limitations for this presentation, let's look only at polymer capsule examples, but please remember, the capsule releases the rejuvenator with the reduced viscosity, and aged bitumen sealing the open depot crack by effect an external trigger. Majorly is a pressure, biolly is a traffic trigger. When you produce capsules, it's very important to design very good emulsions. The emulsion is a combination with the PO polymer, rejuvenator plus water. This is very, very important in order to reach a very good capsule, in this case, polynuclear capsules. At the same time, different physical particles is very interesting to analyze. So creaming index in the emulsions and different properties. The correct design of the pore morphology inside the polynuclear capsule is necessary so that the rejuvenator can be efficiently encapsulated. For example, in this slide, as you can see a CT tomography with the individual polynuclear capsules. Basically, you need design artificial, or you can design in the lab artificial polynuclear capsules with cell healing purposes, inspired by the nature. At the same time, these capsules is necessary to incorporate inside the asphalt mixture during the mixing process. For that reason, mechanical performance of the capsule is so important. We can evaluate in the labs the mechanical compression of the individual capsule to simulate two different modes. The first is the fracture, and the second one is the deformations. Because a polynuclear capsule is like a foam, when you apply pressures, you can release on a small amounts several times. This depends on the traffic. For that reason, you can produce the broken of the capsule with the first mode, and the second mode, you can produce deformation with several times. Different challenge in order to evaluate the cell healing properties in bituminous materials. In this slide, you can see a very beautiful test and pretty easy test in order to evaluate the crack healing over time by using in this case, it's fluorescent microscopy. You can evaluate the close the crack over time in 30 minutes using different rejuvenator or simulation of the deformation of the capsules in the materials. Thermostability condition of the capsule is so important because the asphalt, you can produce asphalt in hot conditions. But it's possible to survive the capsule inside the asphalt mixture, or you can complement the capsule with different solutions in order to increase the mechanical property, in order to increase the thermal resistance. So basically, the capsule resists the asphalt condition, thermal condition exactly, and the capsule resists the asphalt compaction conditions. Several tests using mastic. Mastic is a combination, in this case, is a bitumen plus small pieces, aggregates, and capsules. You can evaluate the rheology properties of the mortar because the mortar is so important in order to evaluate the mechanical behavior of the asphalt mixture in real conditions. We can modify, we can improve the properties using capsules, but you need to incorporate the exactly amount of the capsule in order to, without effects of the asphalt performance. Another challenge is to design new tests in order to stimulate the capsule inside the asphalt mixture. You can design capsules, that's fine. The next is incorporate the capsule inside the asphalt mixture, is correct. But what is the next? The next is activate the capsule under laboratory conditions. For that reason, you need to design a specific test using mildly compression in a static and dynamic condition in order to stimulate the capsule inside the asphalt mixture. After that, you can design different cell heating index by force criteria. You can calculate the curve. You can calculate the area under the curve in order to use the energy, for example. But independent of the heating index, you can increase the cell heating index inside the asphalt mixture. Please remember, the cell healing the bitumen is a cell heating material itself. For that reason, always you need to compare your results compared to the materials without additives. In this case, we can increase up to 20% of the heating index compared to the asphalt mixture without capsules. When they use, for example, the cell heating index using force, this result can be changed when you compare it with the energy. In my previous research, working in University of Nottingham, we produced several tests in order to evaluate the first test in order to stimulate the polynuclear capsule with sunflower oil inside. In this slide, you can see for the different efforts, 1,000 and 1,000 tests with different PhD students. So basically, we can increase the encapsulated rejuvenators, can extend the surface life of the alpha payment by up to 30% without affect the mechanical properties and integrity of the asphalt mixture. This is very difficult to simulate in laboratory conditions. At the same time, you can use CT scan, computer tomography to evaluate the distribution of the capsules inside the asphalt mixture. For example, you can delete, so the different aggregate mastic, you can see here the distribution of the capsules inside the core of the asphalt mixture. You can evaluate the distribution of the capsule. You can evaluate the diameter of the capsule by mixing and compaction purposes. And also, you can evaluate the effectively distribution of the capsule. Basically, the capsule resists the mixture manufacturing process. The capsule breaks inside the mixture by effect of the extrinsic loading, in this case, a static condition or fatigue conditions. The capsule shows a very good distribution inside the asphalt mixture. But what is the next? The next is in order to anticipate for the performance of the capsules. You can use CT scan, but you can use different computational approach in order to design virtual model of the asphalt mixture with different combination of the capsules. You can simulate so the dynamic test using finite element methods in order to evaluate the probabilistic of the number of capsules is possible to activate inside the asphalt mixture in order to increase the cell healing properties inside the materials. In the final part of my presentations, I would like to show you the work in progress. Sometimes it's published. This is an amazing research concerning to design microcapsule with using nature. Basically, we can use natural spore and we can saturate inside our rejuvenators to design microcapsule with properties in order to control the release autonomously. This research was carried out in collaboration with Swansea University and MIT and my colleagues in Chile. In summary, it's possible to design microcapsules with cell-healing properties using the nature. A second example is a collaboration between the Wuhan University and Hertfordshire University in UK. Basically, we can design fibers with rejuvenators with different conditions, with different size, with different properties. And we can design a specific microfluidic device, shapes, basically, in order to design specific conditions. We can combine inside the fiber two different rejuvenators. One rejuvenator for concrete purposes, and the second rejuvenator for asphalt purposes. Everything is possible, unfortunately, in designs. This is my favorite research. Basically, we can use end-of-life turrets and thermochemical conversion, for example, pyrolysis, to produce a specific rejuvenator, specific liquids, in specific components. In the lab, you can increase using different chemical approach the terpenes and monoaromatic components inside the material in order to stimulate the specific molecules inside the asphalt. That is possible. At the same time, it's possible to encapsulate these rejuvenators using biomaterials. You can produce using jet vibration technology. You can produce, for example, polynuclear capsules. You can produce core shell capsules with different purposes. You can evaluate the specific emulsions. You can modify the emulsions with different purposes. At the same time, it's possible to evaluate the mechanical properties of the capsule, not only with specific purposes for asphalt. At the same time, you can incorporate in coating solution for composite materials as well. The rheology of these materials, the combination with the pyrolytic oils or capsule incorporated pyrolytic oil inside, to the capability of the pyrolytic rejuvenator using C-healing index. You can use the DCR test in order to stimulate the sample. You can produce micro cracks, and you heal the cracks autonomously using this material. You can design different healing index, similar to the mechanical test, in order to evaluate, in order to quantify the properties. Basically, we can increase, that's possible, by using this specific rejuvenator based on waste, a problematic industry waste. At molecular level, it's possible to use molecular dynamics to evaluate an important process when you use rejuvenators. The name is diffusion. The diffusion is very, very important because if you can control the diffusion, you can increase the properties of the rejuvenator inside the materials. That is very difficult to evaluate under laboratory conditions using microscopy, for example. it's necessary to incorporate molecular dynamics approach in order to evaluate this phenomena. And you calculate the diffusion coefficient, etc. At the same time, recently, with colleagues from King College London, we have published this data-driven representative model. So basically, we have different biomass ways, probably you can use, Boots, LG, Churchills. And using thermochemical conversion, pyrolysis, hydrothermal liquefaction, it's possible to produce different subproducts. Hydrochar, you can produce bio-crude oil to replace, you can produce bio-asphalt. But when you have this material on your table, you have a problem because it's necessary to the characterization of the materials at molecular level. So basically, you use a different chemical test in order to evaluate the many hundreds molecules inside the material. The main idea of this research is to reduce hundreds of the molecular into a few groups of representative molecular inside the materials from a numerical approach. We can reduce the complexity of the simulation at the same time increase the computational efficiency. But this simulation is so complicated. For that reason, it's necessary to say, Google, please help me. On the Google Cloud, it's possible to simulate these specific materials. For example, in this approach, if we isolate only the phenolic component inside the bioasphalt, let me show you. And basically, we can use the molecular dynamical simulations combined with the different technology, artificial intelligence, to evaluate the interatomic condition inside the material in order to obtain the perfect bioasphalt to replace the bitumen based on petroleum. It's possible to measure to the property prediction, density, viscosity, and other properties. It's possible to design computational approach to replace the normal bitumens because we have, for example, in RILEM, a very big commitment in order to reduce the emission for future. That's possible and necessary. In conclusions, so I would like to highlight 4 different topics. The first is that external heating technology based on metallic waste can extend the surface life of the asphalt pavement by up to 50%. However, this can also affect the physico-mechanical performance of the asphalt mixture. Concerning to the encapsulated rejuvenators based on biomaterials, we have the capacity to extend the surface life of the asphalt pavement about 30% without affect the mechanical properties and integrity of the asphalt mixture. More fundamental research using computational multi-scale approach is needed to understand the asphalt healing process influence for the complex chemical reactions produced by biomass waste. The last, a multidisciplinary collaboration is essential to address the scientific question linked to the asphalt healing for net zero circular economy. To close my presentations, I would like to thank all my collaborators and research agencies that have supported my research in the recent years. Thank you, colleagues. I want to give a special mention to all the members of my former research groups in Chile, LADMAT. Thank you for believing in my ideas and working together towards a common goal. Finally, I would like to express my gratitude to my asphalt research mentors, Alvaro, Eric, and Manfred. Thank you all for your support and mentorship over this year. Thank you very much for your attention.